Bed thickness. For same lithology, joints are more closely spaced in thinner beds. This is because the formation of joints relies a tensile stress in one layer over a lateral distance proportional to the joint length. Since joints end at layer boundaries, which are row discontinuities, the longer joints in thicker layers need to be spaced less frequently. This is this one is weak layer, this is stiff layer, this is very weak layer. This is spacing of bedding parallel joints according to competence elastic modulus of layers. Much work has documented linear relationship between average joint spacing D and bed thickness T. D is equal to alpha T. The slopes alpha are the function of lithology and by inference of mechanical properties. However, this relationship might be valid for beds less than 1.5 meter thick. The slope may change for thicker beds. A continuous curve with a positive slope and a negative second derivative d square capital D by small d capital T square less than 0 acceptably fits all data. Here is the relationship between fracture separation and bed thickness for different rock types from different places. For example, here limestone lies between 0 and 100, 0 and 100 or around it, up to the 100 centimeter mark. Gray wake interlayers greater than 5 centimeter lies between 0 and 400 for for around for 0 to around 50 centimeter apart. Then the gray whack interlayers greater than 5 centimeter for the bed thickness between 0 to 600 centimeter. From 0 to 50 centimeter gray wake interlayers lies. Then from gray wake with interlayers less than 5 centimeter for 0 to 50 centimeter. This is the relationship between fracture separation and bed thickness for different rock types from different places. Lithology. Stronger, more brittle rocks have more closely spaced joints than weaker rocks. Therefore, strong layer fracture lithology. Stronger, more brittle rocks have more closely spaced joints than weaker rocks. Similar rocks with low tensile strength show more joints than stiffer lithologies because the strain is the same along layers of different types. Structure, position, and strain. The structure position, particularly within folds, and the magnitude of seasonal extension strain also controls joint spacing. Wire joints are evenly spaced. Their regular spacing of joints has met several explanations, none of which have been established as a proven mechanism. Pore pressure or porosity interaction. When a joint forms, fluids flow into the fracture and the pore pressure in the joining rock diminishes. Stress shadow exercise explain with a more diagram and any give permeability level how pore pressure variation show controls joint spacing. Stress shadow when a joint forms when a joint forms it relieves the tensile stress on either side of fractured plane that becomes a zero stress surface. Interlayer forces. Each layer is submitted to forces transmitted by adjacent layers. Joints pattern. There are 5 main patterns. Parallel sets are curved or straight. Fan sets along fold or intrusion crush. Radiate sets around intrusion centers. Concentric sets around intrusion and collapse centers. Cone, ring, or cylindrical. Polygonal sets as columnar or prismatic. Master joints. Joints have dimension ranging from tens master joints. Joints that have dimension ranging from tens of centimeters to hundreds of meters and repeat distances of several centimeters to tens of meters are master joints. Besides, most rocks contain numerous inconspicuous joints of smaller size and closer spacing. Some of them, the micro joints or microfracture, visible only in thin section under the microscope. Joint orientation. The permeability of a fractured reservoir is often highly anisotropic because joints generally form in subparallel sets. However, more than one fracture set may be present, resulting in a complex fracture network. Where dips are not obtained, such as on photographs, orientation data are presented on Rose diagram. Joints in given orientation sector, example within 10 degree, are counted. The joint density in the cumulative length over circle's area PF is equal to summation L by pi r square. In general three dimension, this density intensity is the surface area of the joint per unit volume of the rock. Relative timing of joint formation. Joints of same generation have likely the same orientation. This is older joint and opening. This is youngest joint. This is butting relationship between generations with stress perturbation close to pre-existing joints. This is 1 2 3 2. Early joints. This is butting relationship between a joint generation with stress permutation close to pre-existing joints. Early joints tend to be long and relatively continuous. Early joints arrest the propagation and modify the orientation of later ones. Then, as more joints set develop in the rock, modification of stress orientation by the pre-existing fractures may result in poor correlation between the orientation of late joints and the regional stress field responsible for their formation. Consequently, the later joints curve into orientation at a right angle to the earlier ones as they approach them and abut against these abutting relation. Younger joints are consequently shorter. Joint anatomy. Joints normally are barren cracks or empty fissures, but some may contain coatings. Joint surfaces. Barren joints are characterized by clean, granular, and jagged breaks. They are conchoidal structures, meaning that they are uneven structures with low relief convexities and concavities like those of a clamshell and that don't follow any natural plane of separation. Fringe steps. This is fringe face. This is joint tip. This is fringe. This is plumb axis. This is tip line. This is propagation direction. This is plumose marks. This is twist hackle. This is rib mark. This is sigma 1 or sigma 2. This is sigma 1 or sigma 2. This is sigma 3. Surface markings on joint surfaces. Plumose structures. Plumose structures are aggregates of gentle curvilinear undulations. The hackle marks that radiate from the point where the joint originated and fan outward from a generally straight, more rarely curved axial line than resembling the shape and imprint of a feather. The region commonly is some rock heterogeneity such as ripples or on bending planes or inclusions. In bats, hackles are often very fine near the joint origin, while the differential relief may amplify lengthwise towards the joint origin. The fringe hackle diverge sharply at angles of about 30 degrees from the central axis, gradually curving to angles of about 70 degrees near the margins of the joint surface. Rib marks. Rib marks form a series of regular, concentric, and accurate changes or ramps in the orientation of the joint surface, giving cuspate waveforms or ridged ridges or furrows. The central zone of rib marks, the mirror, is often circular or elliptical. Vellner lines are similar to rays, but they occur as one or two sets oblique to the hackles. Strongly asymmetric rib marks with sharp crush and occasionally deviating from parallelism. Arrest marks are associated with slow crack propagation. Interpretation. Plumose and rib marks can be superimposed on joint plane and generally are orthogonal to each other. Such delicate features interlock on opposed surfaces of joints and this precludes shear movement. Hence, joints are mode 1 fractures parallel to the sigma 1, sigma 2. This is log fracture velocity, this is stress, this is rib marks, this is relatively fast propagation velocity, this is slow to intermediate propagated velocity, this is translational markings, this is fast propagation velocity, this is plums and fringes, this is quality distribution of joint surface features with respect to stress intensity and fracture propagation velocity. Joint content. Secondary deposits. The secondary deposits along joints are dilational if the when material occupies space between the two original fracture surfaces, or non-dilational if the vein material occupies space made available by replacement of the original rock outside the two original fracture surfaces. Joint termination and edges. At their fringes, joint surfaces split and twist into small out of plane fractures oblique, typically at 5 to 25 degree, and echelon and an echelon to the main joint. These fringe faces may individually bear secondary pulmose pattern near orthogonal to the direction of propagation of the parent joint. Same fringe test parallel to the joint axis can be segment fringe faces. Mechanics of jointing. A genetic classification of joint is based on the size of interfered imperceptible displacement related to the three principal stress axes of a region. If the total displacement is normal to the fracture surface, it is an extension or dilatant joint. Mode 1 fraction. If the shear component has some finite yet negligible value, the fracture called a shear joint is really a fault. Modes 2 and 3 fracture. Relationship between joints and principal stresses. If we accept an average internal friction angle of 30 degree for general column type failure envelop a 2 theta angle of 135 degree or more diagram, that is a dihedral angle omega is equal to 45 degree between conjugate fractures divides fractures into subclasses. Conjugate fracture enclosing an angle of less than 45 degree involve negative sigma 3 and sigma n when 45 less than equal to omega less than equal to 60 degree. Sigma n is positive although sigma 3 remains negative. This is failure mode. This is class. This sigma minus sigma 3 is diagonal angle. Failure mode. Failure mode if tensile failure, then class extension fracture. Sigma minus sigma 3 less than 40 degree. Dihedral angle 0 degree. Hybrid shear failure. Class extensional shear failure. Sigma minus sigma 3 40 degree to 80 degree. Dihedral angle up to 60 degree. Shear failure. Compressional shear fracture greater than 80 degree. Dihedral angle greater than 60 degree. Note: that there is a relationship between the magnitude of different stress sigma minus sigma 3 and tensile strength T naught of the rock, which is readily seen on moher construction. Block diagram of different fracture types and orientation in compressed experiments on isotropic rocks. This is shear fracture, this is extension fracture, this is shear fracture, this is sigma 1, this is sigma 2, this is sigma 3, this is omega, this is sigma 2, hybrid extension fracture, this is hybrid extension fracture. Then is the failure criterion in Mohr diagram. This is tensile strength T naught, this is 2 T naught, this is 4 T naught, this is 8 T naught sigma n. Sigma tau is equal to sigma s. Cohesion tau naught is equal to 2 T naught. This is stable domain. This is angle of internal friction, which is high. This is unstable domain. Tau is equal to sigma s. This is these are the extension joints. Linear elastic fracture mechanics predicts that the orientation of dilatant joints, general mode 1 fractures, in a readily isotropic is controlled by remote stress field at a time of fracture failure propagation. Joints are gapping parallel to the maximum compressive stress sigma 1 and perpendicular to the direction of the least principal stress sigma 3. In other words, they form in plane containing sigma 1 and sigma 2. This is failure in valve, this is tensile failure, this is sigma n, this is sigma 1, this is sigma 2, this is sigma 3. This is hybrid failure, this is sigma 1, this is sigma 2, this is sigma 3. Sigma 3, there are the directions, opposite directions. But see also here, this is sigma 1, this is sigma 2, this is sigma 3. Here are the directions. This is shear failure. This one is the graph. This one in this diagram, this one is the graph. This is failure in valve. This is tensile failure. Sigma 1, sigma 3. This is hybrid failure. This is sigma 1. This is sigma 3. This is shear failure. This one is the graph. Then is the hybrid joints. Hybrid joints show components of both extension and shear components. Shear joints. This term is unfortunate and ambiguous because shear joints actually are small faults. Conjugate shear joints generally define X, Y, or V shapes. The acute bisector of these shapes is parallel to sigma 1 unless these patterns represent unrelated cross-cutting or abutting fractures. Rock initiation. Geological observation indicates that joints initiate at rock flaws such as fossils, clasts, pyroclasts, cavities, etc. Amplification of small remote tension so that magnitude of local tensile stress at the flaw exceeds the tensile strength of the rock. Conversion of a remote compressional into local tension due to pore pressure. This is joint initiation. Then is the application of remote tension. The reason is that flows have different elastic properties than the rock. For such condition, fracture mechanics consider a circular intrusion and a constant K, the ratio elastic shear modulus of rock upon elastic shear modulus of inclusion. The rock and inclusion have the same Poisson ratio A. Remote tension sigma 3r includes a uniform tension sigma 3i within the inclusion. Then sigma 3i is equal to sigma 3r into 3k over 2k plus 1 and a tangential component sigma t at two opposite points of the inclusion boundary. Sigma t is equal to sigma 3r into 3 over 2k plus 1. Conversion of a compression into tension experiment is the compression have shown that flows can include local tensile stress. For example, for a small angle 2 phi of a grain contact, stress sigma g at the grain center is tensile sigma g is equal to minus sigma 1r into 2 phi by pi at the ends of intrusion diameter parallel to the applied compression sigma 13r. The tangential stress is sigma t is equal to sigma 1 minus sigma t is equal to minus 1 sigma 1r into 1 minus k over 2k plus 1. Then is the conversion of compression into tensile stress on and in particles. Circular gain sigma g, this is 2 phi, this is sigma 1, this is sigma 1, this is sigma t, this is circular inclusion, this is sigma t. Conversion of compression into tensile stress on and in particles. Tension stresses due to pore pressure, fluid pressure asserting the least comparative remote stress produce tensile stress greater than the rock tensile strength, in particular at the extremities of elliptical cavities and micro cracks. Tip propagation fractures may lengthen in direction parallel to the initial plane penetration of the host particle or may deviate from initial fracture orientation, refraction and deflection. Pre-existing discontinuities such as bedding surfaces may interrupt propagation. The former may be the site of stepovers, where two parallel, not coplanar structures were initially outside at the time of their formation. Maximum depth of formation. Assuming that sigma 1 is a vertical near the surface of Earth, uh, it is weight of rocks lessened by the pore pressure Pf. The pore pressure is commonly expressed by fluid pressure ratio. Lambda is equal to Pf by rho gz. Hence, sigma 1 can be expressed as function of the depth z and the rock density rho as sigma 1 is equal to rho gz into 1 minus lambda, with the assumption sigma 3 is equal to t naught is the horizontal and negative. Then is the considering the unique solution for a pure joint on a Mohr plot, that is single point where the failure involves cuts the sigma and axis on its negative side, and that differential stress is related to tensile strength sigma 1 minus sigma 3 greater than 3 t naught. The maximum depth of the formation of a tensile joint is z maximum is equal to 3 t naught over rho g into 1 minus lambda. Taking the standard value of t naught is equal to 40 megapascal. For rocks, the maximum depth of formation of the rock of joints is Ca into 6 kilometer. Inception occurs under high fluid pressure. Then is the T naught. Then is the sigma 1 star is equal to 3 T naught. Then is the unloading joints. Rock possesses elastic property closely related to those measured in laboratory. In non-orogenic environments, uplift and exhumation give rise to changes in the horizontal and vertical stresses, which may exceed the tensile strength of the rock. In particular, hydrostatic confining pressure is released during the decompression, and buried rocks tends to expand gradually. However, difference in compressibility between ocean lithology and mineral grains or different orientation or composition trigger local deviatoric stresses. Sheet exfoli- exfoliation joints. Dialent joints formed during erosion of homogeneous rocks such as granite are parallel to the topography, and these orientation result in sets of flat laying, curved and large, referred to as sheeting or sheet structure. Spacing between sheet joints increases with depth down to 50 to 100 meter. The amount of expansion to be expected from the release of a stored stress consequent on barrier is indicated by values of compressibility of rocks, the ratio of a volume change to pressure change. Bedding parallel and bedding contained joints is such volume changes are accomplished mainly by vertical extension, and if the extension takes place fast enough, horizontal dialects joints may form. Parting of bedding parallel joints is also related to unloading decompression. Joints may also form vertically. Such such bedding such bedding contained joints exhibit different spacing from bed to bed, which likely reflect differences in compressibility between different layers. Weathering along these joints may lead to extreme rounding, which results in boulders. Joints due to non-decompressional volume changes. Stylothelic joints have a characteristic saw-tooth profile and an interdigitating cone-like form in three dimensions. Relative insoluble residues, clay, iron oxides, etc., remained accumulated in the joint. The deformation mechanism is called pressure solution. Styloids are particularly common in the limestone. Then is the owing to this method of displacement, some authors call anti-cracks or mode 4 closing mode fractures. This is styloid orientation with respect to compression. This stylotic joint, these are the pressures. Columnar joints. Columnar joints are the prominent in basaltic sills and lava flows. They form a three-dimensional network of interconnected fractures that dissect the rock in long and specular polygonal common 5 or 6 sided columns. Then is the thermal gradient. This is small column fast cooling. This is coarse colonnade slow cooling. Sketched coursing of columnar joint pattern. The lower part called the colonnade contains regular vertical columns. The center approximately elliptical zone named antablator, often located slightly below the flow center, displays irregular twisted columns expressing rapid convective cooling. The upper zone may be regular columnar, upper colonnade, crudely columnar, pseudo-columnar, or bulky. Mud cracks. Dissection related mud cracks is in sediments are polygonal patterns, ideally hexagonal, similar in many ways to columnar jointing of volcanic rocks. Development of hexagonal joint pattern due to tensile pull towards equally distributed cooling or drying centers with a homogeneous materials. This is shrinking tensile stress. Joints due to regional deformation. If many joints, and particularly those that cut joints due to regional deformation, many joints and particularly those that cut through different lithologies are related directly to faults produced by regional deformation. Veins. Veins are dilated fracture filled with oriented crystal fibers or non-oriented mineral deposit, typically quartz, calcite, or carbonates. Non-fibrous massive crystals generally grow in open cavities, and the veins themselves, sometimes called fault cast veins, which may contain open gas in which hydral crystal terminations glows. Mineral veins occasionally contain economically concentration of metals or other useful elements in ore deposits. Each vein then reflects a single fracture event which is known as crack jump mechanism. Group of veins constitute a vein array. Tension veins. Tension gashes and veins are filled one fractures found in response to combined tectonic and pore pressures. Weak fractures localize subsequent rupture and grow at each cracking step. Healed fractures restore the mechanical strength of systems in which cemented veins tends to remain scaled and new fractures occur in the host rock. This is ankylian veins. This is opening direction parallel to mineral fibers. This is tension gashes. These are the maybe the pressures outward here. Here is the inward vein orientation with respect to compression. Then is the fiber minerals. Elongate infilling mineral crystallize while the veins openings with the long axis of fibers tackling the incremental extension direction. Therefore, fiber minerals track the opening trajectory and document the formation of tension fracture. Three types of internal structure are used are related to shape and orientation of veins with strain orientation. Undeformed fibers are perpendicular to the margin of purely extensional veins. Undeformed straight fibers in shear veins are oblique to the vein margin according to the shear component parallel to the vein walls during vein opening. Fiber crystals often grow at a high angle to the vein wall in a curved shape without any bending or lattice, indicating that the curved shape is a growth feature. Three types of growth direction of vein crystal related to wall rock are identified. Syntactically, inward growth adds material along the center of the vein. Fiber standing from the opposite wall meet at medical sutures, sometimes on one side, where there is both a structure and optical discontinuity. Anti-axial outward growth adds material along the vein wall. Mineral fibers parallel to incremental opening direction of a vein.